Testing, can you hear me? Testing one more time. All right, so I'm going to be learning about computer architecture again. And I'm just going to continue reading from where I last left off. All right. So I was reading about the memory system, and last time I was reading about the hit rate and the. I was reading about the cache. I was reading about the miss penalty and the hit time. This subtopic seems to be about virtual memory. Okay, so let me just zoom in. Up till now, we have considered only one program in our system. We have designed our entire system using this assumption. However, this assumption is not correct. For example, at the moment, there are 232 programs running on your author's workstation. The reader can easily find out the number of programs running on a system by opening the task manager on Windows or by entering the command PSEF on a Linux or Macintosh system. It is possible for one processor to run multiple programs by switching between different programs very quickly. For example, while a user is playing a game, her processor might be fetching her new email. The reason she does not feel any interruption is because the timescale at which the processor switches back and forth between programs, typically several milliseconds, is much smaller than what humans can perceive. Secondly, we have assumed up till now that all the data that our program needs is resident in the main memory. However, this assumption is also not correct. Back in the old days, the size of the main memory used to be several megabytes, whereas users could run very large programs that need hundreds of megabytes of data. Even now, it is possible to work with data that is much larger than the amount of main memory. Readers can easily verify this statement by writing a C program that creates data structures that are larger than the amount of physical memory contained in their machine. In most systems, the C program compile and run successfully. We shall see in this section that by making a small change in the memory system, we can satisfy both of these requirements. Right? Process a running instance of a program. Up till now, we have assumed that the existence of only one program. We have assumed the existence of only one program in the system. We assume that it was not in complete control of the memory system and the processor pipeline. However, this is not the case in practice. Let us first start out by accurately defining the notion of a process and differentiating it from a program. Up till now, we have been loosely using the term program and sometimes using it in place of a process. A program is an array of bytes and is saved as a file in the file system. File is typically known as a binary or an executable. The executable contains some metadata about the program such that its name and type about the program such that its name and type, the constants used by the program, and the set of instructions. In comparison, a process is a running instance of a program. If we run one program several times, we create multiple processes. A process has access to the processor, the peripheral devices, and the memory system. There is a dedicated area in the memory system that contains data and the code of the process. The program counter of the processor points to a location in the code region of the process in memory. Memory values required by the process are obtained from its data region in the memory system. Finally, note that the operating system starts and ends a process and manages it throughout its lifetime. Most people view an operating system such as Windows, Linux, or Mac OS from the point of view of its user interface. However, there is a minor aspect of the operating system. It does many more things invisibly. Let us look at some of its important functions. The operating system consists of a set of dedicated programs that manage the machine. Peripheral devices, and all the processes running on the machine. Furthermore, the operating system facilitates efficient transfer of information between hardware and software components of a computer system. The core component of an operating system is known as the kernel. Its main role is to manage the execution of processes and manage memory. We shall look at the memory management aspect in section 11.4.5. Let us look at the process management aspect. To run a program, a user needs to compile the program and then either double-click the program or write the name of the program, the command line, and click the enter button. Once this is done, the control passes to the operating system kernel, a component of the kernel known as the loader, reads the contents of the program, copies it to a region in the memory system. Notably, it copies all the instructions in the text section, allocates space for all the data, and initializes memory with all the constants that a program will require during its execution. Subsequently, it initializes the values of register, copies command line arguments to the stack, and possibly initializes the stack pointer and jumps to the entry point of the program. The user program can then begin to execute in the context of the running process. Every process has a unique number associated with it. It is known as the PID. After completion, it is the kernel's job to tear down the process and reclaim all of its memory. The other important aspect of process management is scheduling. A dedicated memory component of the kernel manages all the processes, including the kernel itself, which is a special process. It typically runs each process for a certain amount of time and then switches to another process. As a user, we typically do not perceive this because every second the kernel switches between processes hundreds of times. So the kernel manages all the processors, including the kernel itself. All right, the time interval is too small for us to detect. However, behind the scenes, the kernel is very busy at work. For example, it might be running a game for some time, running a program to fetch data from the network for some time, and then running some of its own tasks for some time. The kernel also manages aspects of the file system, inter-process communication, and security. The discussion of such topics is beyond the scope of this book. The other important components in an operating system are device drivers and system utilities. Device drivers are dedicated programs that communicate with dedicated devices and ensure the seamless flow of information between them and user processes. For example, a printer and a scanner have dedicated device drivers that make it possible to print and scan documents respectively. Network interfaces have dedicated device drivers that allow us to exchange messages over the internet. Lastly, system utilities provide generic services to all the processes such as file management, device management, and security. We have the operating system, a set of dedicated programs that manages the machine, peripheral devices, and the processes running on it. Facilitates the transfer of information between the hardware and software components of a computer system. Kernel is a program that is the core of the operating system. It has the complete control over the rest of the processes in the operating system, the user processes, and the processor, and all external devices. It mainly performs the task of managing multiple processes, devices, and file systems. The two important concepts in the kernel to perform process management are the loader and the scheduler. The loader creates a process out of a program by transferring its contents to memory, setting up the appropriate execution environment. The schedules the execution of multiple processes, including that of the kernel itself. Device drivers are dedicated programs that help the kernel and user. These dedicated programs help the kernel and user processes communicate with devices. System utilities, these are generic services provided by the operating system, such as Sprint Queue Manager and File Manager. Since multiple processes are live at the same point of time, it is necessary to partition the memory between processes. If this is not done, then it is not possible that processes might end up modifying each other's values. At the same time, we do not want the programmer or the compiler to be aware of the existence of multiple processes. This introduces unwanted complexity. Secondly, if a given program is compiled with a certain memory map, it might not run on another machine that has a process with an overlapping memory map. Even worse, it will not be possible to run two copies of the same program. Hence, it is essential that each program sees a virtual view of memory in which it assumes that it owns the entire memory system. As we can observe, there are two conflicting requirements. The memory system and the operating system want different processes to access different memory addresses, whereas the programmer and compiler do not want to be aware of this requirement. When a program is compiled, it is not possible to constrain its addresses such that they do not overlap with the addresses accessed by any other process. It turns out that there is a method to make both the programmer and operating system happy. We need to define a virtual and physical view of memory. In the physical view of memory, different processes operate in non-overlapping regions of the memory space. However, in the virtual view, every process accesses any address that it wishes to access. And the virtual views of different processes can overlap. The solution is obtained through a method called paging that we will explain in section 11.4.3. However, before proceeding to the solution, let us discuss the virtual view of memory that a process typically sees. The virtual view of memory is also referred to as virtual memory. It is relative as a hypothetical memory system in which a process assumes that its own entire memory space and that it owns the entire memory space and there is no interference from any other process. Virtual memory system is defined as a hypothetical memory system in which a process assumes that it owns the entire memory space. There is no interference from any other process. Size of the memory is as large as the total addressable memory of the system. For example, in a 32-bit system, the size of the virtual memory is 2 to the power of 32 bytes. Set of all memory locations in a virtual memory is known as the virtual address space. In a virtual memory space, the operating system lays out the code and data in different regions. The arrangement of code, data, constants, and other information pertaining to a process is known as the memory map. The memory map of a process refers to a way an operating system lays out the code and data in memory. You mean within that stack, right? So we start from here, a memory mapping segment, and then the heap. I thought this part goes to the top of the stack. Figure 11.17 shows a simplified view of the memory map of a process in a 32-bit Linux operating system. Let us start from the bottom, lowest address. Shouldn't this be the lowest address? First section contains the header. Okay, they're actually starting from here. Starts out with the details about the process, its format, and the target machine. Subsequently, the header contains the details of each section in the memory map. For example, it contains the details of the text section that contains the code of this program, including its size, starting address, and additional attributes. The text section starts after the header. The operating system sets the program counter to the start of the text section while loading a program. All the instructions in a program are typically contained within the text section. The text section is followed by two more sections that are meant to contain static and global variables. Static variable not initialized, filled with 0. Static variables with initialized values. All right. Optionally, some operating systems have an additional area to contain read-only data such as constants. Text section is typically followed by the data section. It contains all the static global variables that have been initialized by the programmer. It is considered a declaration of the form in C or C++. The static int value 5. Here, the 4 bytes corresponding to the variable val are saved in the data section. The data section is followed by the BSS section. The BSS section saves static and global variables that have not been explicitly initialized by the programmer. But this is initialized, right? Oh, so they're storing it in the data section. Most operating systems fill the memory area corresponding to the BSS section with zeros. This needs to be done in the interest of security. Let us assume that program A runs and writes its value in the BSS section. Subsequently, program B runs. Before writing to a variable in the BSS section, B can always try to read its value. So before writing a variable in the BSS section, B can always try to read its value. In this case, it will try to get the value written by program A. However, this is not a desirable behavior. Wait, hold on. Shouldn't program A and program B have Shouldn't this entire section be different for program A and for program B? Program A should have its own BSS and program B should have its own BSS. This is a memory map of one process, right? So what do they mean when they say program B writing into the same BSS? Program A might have some sensitive data in the BSS section, such as a password or a credit. Do they mean threads in a program? Program B can thus gain access to the sensitive data without program A's knowledge, possibly misuse the data. Hence, it is necessary to fill up the BSS section with zeros such that such security lapses do not happen. Or wait a minute. Do they mean like program A runs, it writes value in the BSS section and then it finishes. And then program B runs, it can read the previously assigned values in the BSS section. I think that's what they meant, right? The BSS section is followed by a memory area known as the heap. The heap area is used to save dynamically allocated variables in a program. C programs typically allocate new data with the malloc call. Dynamically allocating arrays is very useful because their sizes are not known at compile time. The other advantage of having data in the heap is that they survive across function calls. The data in the stack remains valid for only the duration of the function call. After that, it gets deleted. However, data in the heap stays for the entire life of the program, can be used by all the functions in the program, and the pointers to different data structures in the heap can be shared across functions. Note that the heap grows upwards towards higher addresses. Okay. Secondly, managing the memory in the heap is a fairly difficult task. This is because dynamically regions of the heap are allocated with malloc new calls and freed with the free delete calls in high level languages. Once an allocated memory region is freed, a hole gets created in the memory map. It is possible to allocate some other data structure in the hole if its size is less than the size of the hole. In this case, smaller hole gets created in the memory map. Over time, as more and more data structures are allocated and deallocated, the number of holes tend to increase. This is known as fragmentation. Hence, it is necessary to have an efficient memory manager that can reduce the number of holes in the heap. A view of the heap with holes and allocated memory is shown in figure 11.18. We have the fragmentation here. The next segment is reserved for storing data corresponding to memory map files and dynamically linked libraries. Most of the time, operating systems transfer the contents of a file to a memory region and treat the contents of the file as a regular array. This memory region is referred to as a memory mapped file. Secondly, programs might occasionally read the contents of other programs dynamically and transfer the contents of their text sections to their memory map. Such libraries are known as dynamically linked libraries. Is reserved for storing data corresponding to memory map files and dynamically linked libraries. So they treat the contents of a file as a regular array. This is a memory mapped file. Programs might occasionally read the contents of other programs dynamically. Transfer the contents of their text section to their memory map. This is called dynamically linked libraries. The next section is the stack, which starts at the top of the memory map and grows downwards. As discussed in section 3.3.10, the stack continuously grows and shrinks depending on the behavior of the program. Note that figure 11.17 is not drawn to scale. If you consider a 32-bit memory system, then the total amount of virtual memory is 4 GB. However, the total amount of memory that a program might use is typically limited to hundreds of megabytes. Hence, there is a massively empty region in the map between the start of the heap and the data sections. Note that the operating system needs to run very frequently. It needs to service device requests and perform process management. As we just see in section 11.4.3, changing the virtual view of the memory from process to process is slightly expensive. Hence, most operating systems partition the virtual memory between a user process and the kernel. For example, Linux gives the lower 3 GB to a user process and keeps the upper GB for the kernel. Similarly, Windows keeps the upper 2 GB for the kernel and the lower 2 GB for the user processes. Hence, it is not necessary to change the view of the memory as the processor transitions from the user process to the kernel. Secondly, this small modification does not greatly impair the performance of a program because 2 GB or 3 GB is much more than a typical memory footprint of a program. Moreover, this trick does not also conflict with our notion of virtual memory. Program just needs to assume that it has a reduced memory space. Okay. Let us summarize all our discussion up till now. So 2 problems, program and compiler write a program assuming that they own the entire memory space and they can write to any location at will. Unfortunately, the same assumption is made by all processes that are simultaneously active. We have the size problem. Occasionally, we need to run processes that require more memory than the available physical memory. It is desirable if some space in other storage media, such as a hard disk, can be repurposed for storing the memory footprint of a process. This is known as the size problem. To balance the requirements of a processor, operating system, compiler, and programmer, we need to design a translation system that can translate the address generated by a process into an address that the memory system can use. By using a translator, we can satisfy requirements of the compiler, of the programmer / compiler who need virtual memory and the processor memory system who need physical memory. Translation system is similar to what a translator in real life would do. For example, if you have a Russian delegation visiting Dubai, then we need a translator who can translate Russian to Arabic. So processors use a virtual address, and then the address translation system translate it to a physical address. Let us try to design this address translation system. Let us first succinctly list the requirements that a program and compiler place on the nature of virtual memory. Any address in the range of valid addresses should be accessible. For example, in a Linux-based machine, a process's virtual memory size is limited to 3 GB. Hence, it should be possible to access any address in this range. The virtual memory should be perceived as one contiguous memory space where the entire space is available to the program. Unless explicitly desired by the program, there should be no interference from any other program. Here are the requirements from the side of the memory system. Different programs should access non-overlapping sets of addresses. A program cannot be allocated large contiguous chunk of memory addresses. This will cause a high degree of wastage in space due to fragmentation. If the total amount of physical memory is less than the size of the virtual memory, then there should be additional storage space available to support programs that require more space than the total amount of physical memory. Let us now try to satisfy these requirements by designing a translation system that takes an address as specified in the program and translates it to a real address that can be presented to the memory system. The address specified in the program is known as the virtual address, and the address sent to the memory system is known as the physical address. We can trivially achieve a translation system by uniquely mapping each virtual address to a physical address at the level of every byte or memory word. In this case, the program receives one contiguous memory space. Secondly, we need to only map those virtual addresses that are actually used by the program. If a program actually requires 3 MB of space, then we end up using only 3 MB of physical memory. Whenever the process requires a new set of bytes that have not been already mapped, a smart memory management unit can allocate new space in physical memory. Lastly, note that it is necessary for every memory access to pass through this translation system. Even though our basic translation system satisfies all our requirements, it is not efficient. We need to maintain a large table that maps every byte in the virtual address space to a byte in the physical address space. This mapping table between virtual and physical addresses will be very large and slow. It is also not very power efficient scheme. Secondly, our scheme does not take advantage of spatial and temporal locality. Hence, let us try to make our basic system more efficient. Pages and frame. Page is a block of memory in the virtual address space. Frame, a block of memory in the physical address space. Page and frame has the same size. In a page table, it is a mapping table that maps the address of each page to an address of the frame. Each process has its own page table. Instead of translating addresses at the granularity of bytes, let us translate addresses at the granularity of larger blocks. This will reduce the amount of state that we need to maintain. And to take advantage of spatial locality, let us define a block of memory in a virtual address space and call it a page. Similarly, let us define a block of the same size in the physical address space and call it a frame. The size of a page or frame is typically 4 kilobytes. Secondly, note that the virtual address space is unique to each process, whereas the physical address space is the same for all processes. For each process, we need to maintain a mapping table that maps each page to a frame. This is known as the page table. A page table can either be implemented in hardware or in software. A hardware implementation of the page table has dedicated structures to store the mapping between virtual and physical addresses. The lookup logic is also in hardware. In the case of software implementation, the mappings are stored in a dedicated region of the physical address space. In most processors that use software page tables, the lookup logic is also in hardware. They typically do not use custom routines in software to look up page tables because this approach is slow and complicated. The lookup logic of page tables primarily in hardware, the design of page tables need to be relatively simple. Page tables that we describe in the next few sections are oblivious to how they are implemented. It is considered a 32-bit memory address. We can now split it into two parts. If we consider a 4 KB page, then the lower 12 bits specify the address of a byte in a page. This is known as the offset. The lower 12 bits specify the address of a byte in a page. Wait, hold on. Because 12 bits is 4 kilobytes, we only need the lower 12 bits, right? And they're 32 bits in total. The upper 20 bits specify the page number. So the page number is like which I forgot what's page number. I think which process it belongs to. Or no, which block it belongs to. Likewise, we can split the physical address into two parts: frame number and an offset. Process of translation as shown in figure 11.21 first replaces the 20-bit page with an equivalent 20-bit frame number. Then it appends the 12-bit offset to the physical frame number. So the relative offset within those 4 kilobytes should be the same, right? See figure 11.21. Page number offset. Page number specifies the block, right? Which block? Page table and then frame number offset. And then the page table converts the page number to the frame number. Figure 11.22 shows a basic page table that contains 2 to the power of 20 rows. Each row is indexed by a page number and it contains the corresponding 20-bit frame number. The total size of the table is thus 2.5 megabyte. If we have 200 processors on the system at any point of time, then we need to waste 500 megabyte of precious memory for saving page tables. If our total main memory is 2 GB, then we are spending 25% of it in saving page tables, which appears to be a big waste of space. Secondly, it is possible that in some systems, we might not even have 500 megabyte of main memory available. In this case, we cannot support 200 live processes at the same time. We need to look for better solutions. So wait, let me see. Total size of the table is thus 2.5 megabytes. If you have 200 processors running in the system, then we need to waste 500 megabytes for page tables. We are spending 25% of it in saving page tables, which appears to be a big waste. Alright, 2-level page table. Let us further split a page table into 2 equal parts. We split the 20 bits into 2 parts containing 10 bits each as shown in figure 10.23. Okay, 10, 10. The upper 10 bits are used to access a top-level page table known as primary page table. Each entry in the top-level page table points to a secondary page table. An entry in the secondary page table contains the frame number. If no address is mapped to a given entry in the primary page table, then it does not point to a secondary page table, and thus there is no need to allocate space for it. If no address is mapped to a given entry in the primary page table, then it does not point to a secondary page table. Okay. So the primary page table contains 1024 entries where each entry is 10 bits long. Total size is 1.25 kilobyte. Let us number the secondary page table. Let the number of secondary page tables be n. Each secondary page table contains 1024 entries where each entry is 20 bits long. Therefore, the size of each secondary page table is 2.5 kilobyte. Total storage requirement is 1.25 plus 2.5 times n kilobytes. Because of spatial locality in a program, n is not expected to be a large number. It is considered a program that has a memory footprint of 10 megabyte. It contains roughly 2,500 pages. Each secondary page table can map at most 1024 pages. It's highly likely that this program might map to only 3 secondary page tables. 2 page tables will contain the mappings for the text, data, and heap sections, and 1 page table will contain the mappings for the stack section. In this case, the total storage requirement for the page tables will be equal to 8.75 kilobyte, which is very reasonable. Anyway, even if we require double the number of secondary page table because of lower spatial locality in the memory map, then also the total storage requirement is equal to 16.25 kilobyte. This is an order of magnitude better than a single level page table that require 2.5 megabyte of storage per process. Hence, 2-level page tables are used in most commercial systems. Wait, hold on. The upper 10 bits are used to access a top-level page table. Okay. Each entry in the top-level page table points to a secondary page table. So for every process, hold on. An entry in the secondary page table contains the frame number. If no address is mapped to a given entry in the primary page table, then it does not point to a secondary page table. So every process would have the same upper 10 bits, right? Is that what they're saying? Otherwise, they won't be able to match to a particular frame number. So only the bottom 10 bits where they differ, right? Some processors, such as the Intel Itanium or PowerPC 603, use a different design for page table. Instead of addressing the page table using the page number, they address and use the frame number. In this case, there is only one page table for the entire system. As one frame is typically uniquely mapped to a page in the process, each entry in this inverted page table contains the process ID and the page number. So let's see inverted. We put the frame and the page number. In this case, there is only one page table for the entire system. Since one frame is typically uniquely mapped to a page in a process, since one frame is typically uniquely mapped to a page in the process, each entry in this inverted page table contains the process ID and the page number. Figure 11.24a shows the structure of an inverted page table. The main advantage of an inverted page table is that we do not need to keep a separate page table for each process. In their space, if there is a lot of processes and the size of the physical memory is small. Since one frame is typically uniquely mapped to a page in a process, each entry in the inverted page table maps to the process ID and the page number. Okay. The main difficulty in inverted page tables is in performing a lookup for a virtual address. Scanning all the entries is a very slow process and is thus not practical. Hence, we need to have a hashing function that maps process ID and page number paired to an index in a hash table. This index in the hash table needs to point to an entry in the inverted page table. Since multiple virtual addresses can point to the same entry in the hash table, it is necessary to verify that the pair matches that stored in the entry is in the inverted table. So wait, since multiple virtual addresses can point to the same entry, it's necessary to verify that the pair matches that stored in the entry in the inverted page table. Wait, if am I reading this right? It is necessary to verify that the process ID page number pair matches that stored in the entry in the inverted page table. Okay, we can show one scheme for using an inverted page table in figure 11.24b. After computing a hash of the page number and a process ID pair, we access a hash table index by the contents of the hash. The contents of the hash table entry point to the frame F that might map to a given page. However, we need to verify since it is possible that the hash function maps multiple pages to the same frame. We need to verify that the hash function maps multiple pages to the same frame. Okay. Wait. So let's see the pair, hash engine, hash table, and then inverted page table. Compare the page number process ID with each entry. Subsequently, we access the inverted page table and access the entry F. An entry in the inverted page table contains the page number and process ID pair that is mapped to a given entry. We find that the contents do not match, then we keep searching for the page number process ID pair in the subsequent k entries. This method is called linear probing. I think I know what they're doing. So their hash might map to multiple frame numbers, right? And they're using the inverted page table to see if a particular match is correct. We do not get a match within k entries, then we may conclude that the page is not mapped. You then need to create a mapping by evicting an entry similar to caches and then writing it to a dedicated region in main memory that buffers all the entries that are evicted from the inverted page table. We need to always guarantee that the entry pointed to by the hash table and the actual entry that contains the mapping do not differ by more than k entries. If we do not find any free slots, then we need to evict an entry. An astute reader might argue that you can directly use the output of the hashing engine to access the inverted page table. Typically, we add accessing the hash table as an intermediate step because it allows us to have better control over the set of frames that are actually used. Using this mechanism, it is possible to disallow mappings for certain frames. These frames can be used for other purposes. Lastly, we need to note that the overheading of maintaining and updating hash tables outweigh the gains in having a system-wide page table. Hence, an inverted page table is typically not used in commercial systems. For every single memory access, it is necessary to look up the page table for translating the virtual address. The page table itself is stored in physical memory, hence we need to do a separate memory access to read the corresponding entry of the page table. This approach doubles the number of memory accesses and is thus very inefficient. However, we can minimize the number of extra memory accesses by maintaining a small cache of mappings in the processor. We typically use a structure known as the translation locusite buffer, that is a small, fully associative cache. A TLB contains 32 to 64 entries. Each entry is indexed by the page number and contains the corresponding frame number. Once a memory address is calculated in the EX stage of the pipeline, it is sent to the TLB. The TLB is a very fast structure, and typically its access time is a fraction of a cycle. There is a TLB hint that the physical address is ready by the time we reach the memory access stage. Memory access stage of the pipeline can then issue the read-write request to the memory system using the physical address obtained from the TLB. However, if there is a TLB miss, then the pipeline needs to stall and the page table needs to be accessed. This is a slow process and takes tens of cycles. Fortunately, the hit rate of the TLB is very high in most programs because of two reasons. First, programs have a high degree of temporal locality. Second, a 64-entry TLB covers 256 kilobyte of the virtual address space. The working setting of most programs fits within this limit for small windows of time. We have solved the first problem, ensuring that processes do not overwrite each other's data. Now we need to solve the second problem, which is to ensure that a system can run even when the memory footprint of a program is more than the amount of physical memory. For example, we might need to run a program within the memory footprint of 3 GB on a machine, 2512 megabyte of main memory. Even on regular desktop machines, it is possible that the combined memory footprint of all the processors is more than the size of the main memory. To support this requirement, we need to find a location to save all the data that does not fit in the main memory. Most processors typically have a peripheral devices connected to the processor, such as a hard disk or a USB flash drive, that have a large amount of storage capacity. We will study about storage devices in detail in chapter 13. In this section, we only need to appreciate the following aspect of such connected storage devices. So connected storage devices are very slow. The access time to main memory is about 100 to 300 nanoseconds, whereas for hard disk it's in order of milliseconds. Storage devices typically have several orders of magnitude more storage than main memory. They are conceptually treated as a large array of bytes, similar to the way we treat main memory. However, an address in the memory system is unrelated to the address in the hard disk. Storage devices are not part of the main memory. It is not necessary to have a storage device physically close to the processor. It can be accessible over the network or be in another part of the world. A storage device can define an area known as the swap space that has space to contain all the frames that cannot be saved in main memory. Furthermore, this storage region need not be a superset of the main memory. If it is an extension of the main memory, then we can define a larger physical memory. For example, if we have 2 gigabyte of main memory and 3 gigabyte of swap space, then the total amount of physical memory can be 5 gigabyte. In this case, if we need to displace a frame from main memory, then we need to allocate a location for it in swap space. Alternatively, the swap space can be inclusive. In the above example, we need to effectively have 3 gigabyte of physical memory. The main memory acts like a cache for the swap space. In either case, the role of the swap space is to increase the amount of available physical memory. Now the obvious question that arises is, how does the memory system know if a frame is present in main memory or the swap space? We can argue each entry in the page table with an extra bit. We can augment each entry in the page table with an extra bit. If this bit is 1, the frame is in the main memory, hence it is in the swap space. Now this system can be made more complicated also. Instead of one swap space, we can also have multiple swap spaces and use multiple bits in a page table entry to indicate the corresponding swap space. Up till now, we have not discussed how page tables are actually managed and stored. That is considered a typical life cycle of a process. When a process begins, the kernel allocates a primary page table in main memory and clears off the TLB. Okay, it can then insert the mappings for the text and data sections. Secondly, the kernel can optionally allocate some space and insert some mappings for the heap and stack sections. As long as there's a TLB hit, there's no problem. Once there's a TLB miss, it is necessary to access the page tables. Secondly, the pipeline needs to stall. The job of accessing the page tables is typically handled by a dedicated unit known as the memory management unit. It can either be a hardware structure or a software structure. If it is a hardware structure, then we have a dedicated logic in the processor. Otherwise, it is necessary to invoke the MMU process by suspending the current process. In other case, the operation of the MMU is the same. It needs to first locate the starting address of the primary page table. Note that this address cannot be a virtual address, otherwise we will need a page table for a page table. Hence, we need to directly use physical addresses in this case. This starting address is kept either in the dedicated processor register or in dedicated locations of physical memory. The MMU needs to access the appropriate entry in the primary page table and get the address of the secondary page table. The address of the secondary page table is another physical address. If the secondary page table exists, then the MMU accesses the relevant entry in the secondary page table, gets the frame number. Subsequently, it evicts an entry from the TLB and adds the new mapping. We're going to follow an LRU replacement scheme described in section 11.2.5. Note that it is necessary to have all page tables in the main memory. They cannot be in soft space. There are several things that can go wrong in this process. If a page is being accessed for the first time, it is possible that it might not have a secondary page table or its corresponding entry in the secondary page table, or its corresponding entry in the secondary page table might be empty. In this case, it is necessary to find free frame in main memory, create a secondary page table if required, and then insert mapping in the secondary page table. To find a free frame in memory, the MMU must maintain information about each frame. This information can be kept in the form of a bit vector where each bit corresponds to a frame in main memory. If it is free, then the bit is 0, else if it is mapped, then the bit is 1. If a free frame is available, then it can be used to map the new page. Otherwise, we need to forcibly free a frame by writing its data to a swap space. The method of finding a frame to evict from main memory is known as the page replacement policy. Subsequently, we need to change the page table entry of the page that we previously mapped to this frame. It needs to now say that a page is available in the swap space. Once a frame has been freed, it can be mapped to another page. Alternatively, it is possible that the entry in the page table indicates that the frame is there in the swap space. In this case, it is necessary to bring the frame into main memory. You first need to find a free frame, or if necessary, a vector frame from main memory. Then we need to create an appropriate page table mapping. So, whenever a page is not found in main memory, the event is known as a page fault. It is subsequently necessary to create appropriate mappings in the page table and fetch the data from the swap space. Fetching an entire page from the swap space is a rather slow process and takes millions of cycles. Hence, it is very important for the MMU to manage pages efficiently. In specific, the page fault rate is very sensitive to the page replacement policy. Similar to a cache block replacement policy, we can have different kinds of page replacement policies such as FIFO and LRU. For more information on page replacement policy, the reader, memory access, TLB hit, send mapping to processor, page table hit, populate TLB, send mapping to processor, reframe available, evict a frame to swap space, update its page entry table. Read in the new frame from swap space if possible, or create a new empty frame. Create update mapping in the page table, populate TLB, and send mapping to processor. It turns out that we can do several interesting things with page table mechanism. Let us look at a few examples. Shared memory. Let us assume that two processes want to share some memory between each other, such that they can exchange data between them. Then each process needs to let the kernel know about this. The kernel can then map two pages in both the virtual address space to the same frame. Now each process can then write to a page in its own virtual address space, and magically the data will get reflected in the virtual address space of the other process. Sometimes necessary for several processes to communicate among each other, shared memory mechanism is one of the fastest methods. Computer viruses typically change the code of a running process such that they can execute their own code. This is typically achieved by giving a specific sequence of erroneous inputs to a program. If appropriate checks are not in place, the value of a specific variables whether the program gets overwritten. Some variables can get changed to pointers to the text section, and it is possible to exploit this mechanism to change instructions in the text section. It is possible to solve this problem by marking all the pages in text section as read-only. It will thus not be possible to modify their contents in runtime. We have been assuming that a program is free to lay out the memory map according to her wish. She might, for example, decide to start the stack at a very high address such as this. However, this code might not run on a machine that uses 16-bit addresses, even if the memory footprint of the program is very small. Secondly, it is possible that a certain system might have reserved some parts of a virtual memory and made them unavailable to the process. For example, operating systems typically reserve the upper 1 or 2 GB of the kernel. To solve these problems, we need to create another virtual layer on top of the virtual memory. In segmented memory, there are specific segments of segment registers for the text, data, and stack sections. Each virtual address is specified as an offset to these specific segment register. By default, instructions use the code segment register and data uses the data segment register. The memory access stage of the pipeline adds to the offset to the value stored in the segment register and to generate the virtual address. Subsequently, the MMU uses this virtual address to generate the physical address. Okay, now it's going for summary and exercises. Okay, I'll have to go, so I will end the stream here. Wait, let me see what is the other chapter. The other chapter is about multiprocessor systems. I think there are 2 chapters left. I might read this. I'm not sure. The last one is about IO and storage devices. Like after I finish this book, I do have plans. I want to focus more on math. I want to focus more on some math books. and then go back to computer science. Anyways, I will end the stream here, and yeah, I will see you guys next time. Bye.